Almost all the power we use, like 99% of it worldwide. The electricity for the studio for your phone charging right now, it runs on a principle figured out way back in the 1830s.
Yeah, it's pretty amazing. We're talking about Michael Faraday and Joseph Henry's work.
It really is astounding. Our super modern world, totally dependent on physics from nearly 2 centuries ago.
It is. And that core idea is electromagnetic induction. If you really want to get where electricity comes from, you need this basic concept. Electricity, magnetism, they have this sort of two-way street. Change your magnetic field, and, well, you induce an electric current.
So that's our mission today. Take that fundamental piece of physics induction and see how it scales up to, massive power plant. And then how we manage all that energy. We've looked at sources on the physics, the generator tech, and, crucially, transformers. Okay, let's unpack this.
Right, so we could probably skip the absolute basics, like just moving a magnet near a wire.
Yeah.
The really critical part is that the voltage you induce, that electrical push, it completely depends on how fast the magnetic flux changes.
Ah, the rate of change.
Exactly. It's not just about if the field changes, but how quickly and how often you sweep that field past the wire or the wire through the field.
Okay, so the speed of the change, that's where the power comes from. That makes sense then why our grids pretty much all use alternating current AC. If the field has to keep changing, well, rotation seems like the obvious way.
Precisely. Generators naturally produce AC because they're built on rotation. Think of a loop of wire spinning in a magnetic field. As it turns, the induced voltage and current. They're constantly shifting, not just how strong they are, but which direction they're flowing.
And that gives you that smooth up and down wave, the sine wave we see in diagrams.
That's the one. It's the signature of AC.
And that oscillation, that back and forth, is fundamental. Our sources mention that grids standardize this frequency, this flipping rate, though interestingly, not everywhere uses the same standard. Like here in the US, it's typically 60 hertz, right? 60 cycles per second. But then places like Turkey use 50 hertz. It's a technical difference from way back when, but the physics, the rotation causing induction, that's identical.
Absolutely. And we shouldn't gloss over the need symmetry here. A generator takes motion, mechanical energy, and turns it into electrical energy using induction.
Okay.
A motor does the exact opposite. It uses electricity to create motion, to create rotation.
Yeah.
Same principles, often very similar designs, just running the process, forwards or backwards.
This is where it starts getting really interesting for me scaling this up. City-level power. If rotation is the key, how do you go from a tabletop demo to generating megawatts? Let's talk about the big one, the turbo generator.
Right, the turbo generator. That's a classic workhorse of the power grid. It takes that rotation idea and just makes it massive. You use some heat source, could be burning coal, nuclear reaction, natural gas, boil water into high-pressure steam.
Okay, so you need steam first.
Yeah, powerful steam. And that steam blasts against huge turbine blades like a giant pinwheel. Those spinning blades turn the armature, which is just enormous coils of wire inside a really strong magnetic field. It's basically brute mechanical force, spinning those coils to induce current founder, based purely on Faraday's law.
So it almost doesn't matter how you get the initial energy, burning coal, splitting atoms, even hydropower from a dam. The end game is always just to create that rotation, spin the coils, make electricity via induction.
That's the core of it for most large-scale generation. But, that reliance on spinning metal parts, it brings up an engineering challenge.
Yeah.
How do you push efficiency higher when you're limited by friction, heat, the physical stress on moving parts?
Right, there have to be limits.
Which leads engineers to explore more advanced ideas like the magnetohydrodynamic generator, MHD.
Magnetohydrodynamic?
Yeah.
Okay, that sounds pretty futuristic. If you get rid of the spinning coils, the armature, what's left to conduct the electricity?
You replace the solid metal conductor with a fluid conductor. Specifically, a super hot, really fast-moving stream of ionized gas, plasma.
Plasma, like in stars.
Essentially, yes.
Yeah.
This plasma is very conductive because it's full of free-floating positive and negative ions. So instead of spinning a wire through a magnetic field, you shoot this stream of plasma through a powerful magnetic field that isn't moving.
And what happens when that charged gas hits the stationary magnetic field?
Well, the magnetic field exerts a force on those moving charges, the ions. It pushes the positive ions one way and the negative ions the other way. It separates them.
Ah, creating a voltage difference.
Exactly. You get a buildup of positive charge on one side, negative on the other. You place electrodes there to collect these separated charges, and boom, you get a direct current flowing.
That's clever. You bypass the need for all those large, heavy, rotating components that can wear out or melt.
And that's the big potential advantage. MHD generators can handle incredibly high temperatures, temperatures that would destroy conventional turbine parts. This means, theoretically, they can be much more efficient at converting heat into electricity.
But there's always a but, isn't there?
Well, yeah, managing extremely hot reactive plasma is technically very challenging. So while the physics is sound and promising, most MHD applications right now are still kind of specialized or in the experimental phase. It's not replacing turbogenerators wholesale just yet.
Okay, so we've got ways to generate the power spinning turbines or shooting plasma, but that power isn't useful if it just stays at the power plant. It needs to get to us. You said the generator makes the power, but the transformer manages it. How crucial is this thing?
Oh, absolutely critical. You couldn't have the modern power grid without the transformer. Simple as that. It's this silent device that lets us change the voltage and current levels of AC power. Step it up, step it down.
And crucially, it only works with AC, right? Because it needs that changing field.
Precisely. Just like the generator relies on change, the transformer does too. No change, no induction, no transformation. It needs that alternating current.
Okay, so how does it work? No moving parts this time.
It's pure induction, but shared between two coils. You have a primary coil and a secondary coil, both wrapped around a common core, usually made of laminated iron to guide the magnetic field.
Right.
AC flows into the primary coil. That creates a constantly changing magnetic field inside the core. Because the core links both coils, this changing field passes through the secondary coil as well and induces an AC voltage in it.
And changing the voltage is just about how you build it, like how many turns of wire.
Exactly that simple, conceptually. The ratio of the voltage in the primary coil to the voltage in the secondary coil is directly proportional to the ratio of the number of wire turns in the primary coil to the number of turns in the secondary.
So if you want to boost the voltage way up...
You've seen way more turns on the secondary coil compared to the primary. It's elegant, really.
But you mentioned there's no free lunch in physics. You step up the voltage, something else must change. Power conservation, right? The trade-off.
Yes, the trade-off is key. In a perfect transformer, the power going in equals the power coming out. And power is voltage times current. P equals V, I guess, I. So if you increase the voltage, say, you step it up by 100 times.
The current has to drop by 100 times to keep the power the same.
Exactly. And that is why transformers are essential for sending power over long distances. High voltage means low current for the same amount of power. And low current means much, much less energy wasted as heat just from the resistance in the power lines themselves. It's all about efficiency.
Okay, that makes sense. But I'm thinking about those coils again. Doesn't the changing current in a coil affect the coil itself? Something called self-induction?
Good point. Yes, self-induction or just inductance is an inherent property. When the current flowing through a coil changes, it induces a voltage in that same coil. And this induced voltage always acts to oppose the change that created it.
So it sort of fights back against the current changing.
In a way, yes. It introduces a kind of electrical inertia. It's why, for example, if you suddenly break a circuit with a big coil in it, you might see a spark jump across the switch.
Oh.
That's the coil trying to maintain the current, inducing a high voltage to fight the sudden drop. Engineers have to account for this inductance in designing generators, transformers, and entire circuits.
Okay, zooming back out. We generate power, often using rotation. Then right away, we use transformers to step the voltage way up. Like how high are we talking?
Really high. Transmission lines can operate anywhere from, say, 25,000 volts up to maybe 750,000 volts. Huge numbers. All to minimize those resistive losses during long-distance travel.
And then, closer to our homes and businesses, more transformers step it back down.
Exactly. In stages. A local substation might drive it down significantly, and then those smaller, often gray or green transformers you see on poles or pads near houses, they do the final step down to the voltage you actually use, like 220 volts or 120 volts, depending on where you are. The transformer is the gatekeeper, making high voltage transmission practical and safe for end use. And, thinking bigger picture again, discovering induction wasn't just about making power plants. It fundamentally changed our understanding of physics. It pointed towards this incredible symmetry in nature.
Right, we started with Faraday. Changing magnetic field makes an electric field.
And then James Clerk Maxwell came along and, using mathematics, showed the reverse is also true. A changing electric field creates a magnetic field.
Wow, perfect symmetry.
It is. And this unified theory of electromagnetism, Maxwell's equations, it didn't just link electricity and magnetism. It predicted something entirely new, which electromagnetic waves. The idea that these changing electric and magnetic fields could sustain each other and travel through space at the speed of light, which it turns out is exactly what light is. And radio waves, X-rays, they're all just different frequencies of these electromagnetic waves, all stemming from that fundamental link.
Okay. So what does this all mean? We've gone from Faraday spinning a wire near a magnet to these giant turbogenerators using steam power, even looking at futuristic MHD generators using plasma. We saw how induction is the key engine. And then the transformer, this essential device that steps voltage up and down using those same induction principles, making our entire electrical grid possible and safe.
So maybe a final thought to leave you with. Consider this. The next time you flip a light switch, charge your phone, or even just see a power line overhead, remember that our whole electric age is built on this principle of induction, essentially. Needing to physically move something, whether it's a coil or plasma, through a magnetic field. That reliance on motion and materials, that's still the fundamental constraint. The beautiful physics Faraday and Maxwell uncovered gave us electricity, yes, but it also locks us into needing rotation, needing turbines, needing fuel or force to create that movement. The really big challenge for the future. Maybe it's finding a way to generate useful power without relying on bulk motion at all. A breakthrough that taps into physics, perhaps quantum physics, in a way that bypasses the limits of the classical generator entirely. And that would be a revolution.